Smart sensors with embedded edge preprocessing are the base of predictive maintenance for process manufacturing. Sensors Expand Conference, June 2019, San Jose, California. Principal CTO of Terry Automation. This speech is about smart sensors with embedded edge preprocessing. The first part of this speech is about issues that you probably know. So we're gonna go fast over them just to make a quick review, and then we're gonna show some examples, and even I think I have something like 5 or 6 videos with practical examples of what we have done with different sensors in industrial applications, which is probably going to be the most interesting part of the speech today. Okay, the first slide, it's a session summary. We're going to talk about predictive maintenance versus preventive, and its role in condition monitoring, creating a digital twin as a replica, how to use sensors to acquire the physical variables, the preferred types of sensors for industrial IoT, what we call the Big Six, and discrete data versus continuous data, the connectivity problems, what we call the bandwidth culprit, the problems at the database, like the space, the unstructured data, and the garbage at the database. And we're going to talk about our proposed solution, which is, of course, preprocessing at the sensor edge, how it resolves the practical problems of implementing Industry 4.0 projects. We're going to show some case studies with product quality on a steel plant with videos, some other problem with laser processing in a textile plant, wind generators, and some other examples with automotive plants and electrical transformer substations. We will see that in a minute. Condition-based predictive maintenance is not a new subject. It's really been here since the 80s. But there is a new modern approach using IoT, such as modern sensors and connectivity, and the lower price of hardware today makes everything different. Also, new, more powerful microcontrollers make preprocessing possible right at the sensor edge. That was not possible just 10 years ago. And we're going to see how predictive maintenance is built upon data. In fact, we will see that data and quality data is the most important requirement for good predictive maintenance and to build prediction models. Maintenance is the key factor to solve production downtimes. Modern predictive maintenance is a new branch of data science. And we're going to go about that because the problem of machine learning models that don't work is one of the issues that we are resolving with preprocessing. Predictive maintenance is a multidisciplinary field where hardware engineers work with designing the sensors, and firmware engineers design the embedded edge preprocessing. Connectivity experts work with the wireless solutions, and high-level software developers work on the server side, and artificial intelligence and data scientists work in the creation of prediction models. 1 minute of stop production downtime costs an average of $20,000 in the automotive industry. We have checked these figures with some manufacturers in the automotive industry, and it's a true number, and that's Nielsen research. And of course, a stop production line costs a lot of money each minute. Okay, something that happened when getting into real projects is that sometimes we talk with the IT department and we ask them, did you talk with the planning engineers? Oh no, should we? Of course you should. I mean, the planning engineers, they have they're in contact with the machinery. They know what's more prone to break down, to failure. So of course, talking with them, it's a very important part of the process of putting, a prediction model to work. So don't forget about that. Sometimes it's hard because plant engineers, they're like in a different world, they work in a different world, but this is very important. The benefits of predictive maintenance, well, this is something that you can find on Google, so I'm not gonna stress over it. I will highlight the reduction of production cost and minimizing the environmental impact as the two key factors to implement predictive maintenance in the factory. Okay, creating the digital twin. The digital twin, and this is a digital twin image. The factory is on the left side, and then the energy is here. You see that the machinery has different colors, and as we can see, what is actually showing up here is the straight energy of the machinery. And actually what we are acquiring with the most important sensors is that lost energy. In the case of acoustic emission by ultrasound analysis, it's the stress energy. In the case of thermal imaging, it's the heat energy. And in the case of vibration sensors, it's the kinetic energy that is being lost in the machinery. This virtual model is a replica of what is happening in the factory. And we're going to see how we create a digital twin, putting the right sensors in the right places, with the target of producing quality data. And we will see how better quality, and the longer we're recording the data, the better is going to be the model that we can create. So the digital twin works by installing multiple sensors that read multiple variables. One or two sensors are not good enough, are very rarely good enough. You have to put a lot of sensors, different sensors, and we're going to see with the Big Six what sensors are the most, have the best use on industrial use, on industrial applications. Of course, in industry, reading in real time is paramount. And in our approach, solutions like sampling temperature sensors every 10 minutes or by the hour make no sense whatsoever in industrial IoT. We need real time. And comparing readings of different sensors with technology that's usually called sensor fusion, which you can see here. This is an example with acoustic energy by ultrasound analysis, lubrication, vibration, and temperature by infrared. Well, this technology is actually coming from the aerospace industry. This is what the inertial navigation units on airplanes do with different sensors like the pitot tube, which measures the speed of the air and the attitude. So like in the airplane example, the idea here is to study the data from different sensors in time synchronization with a precise timestamp in a way that it gives a more comprehensive view of what is going on in the factory. Okay, smart industrial sensors. I'm gonna start talking about how smart industrial sensors are built, what are the Big Six, the most important physical variables to acquire in industry. Okay, here we have some definitions. A sensor is a device that provides information on the physical variable of a process or substance in a predictable, consistent, and measurable way. I'm going to stress that there is no sensor prescription to predictive maintenance. Each industry, each case, each problem is different, and we're gonna see that we're gonna have to use different sensors in different projects. Each case is just plainly different. Also, today there are many sensors on the market. There are transducers to quantify almost any variable: gases, vibration, corrosion, thermal, current, pressure, you name it. Today, with all those transducers, we have the tools to make a good job on reading those physical variables. What happens is that in many projects, a percentage of the sensor had to be custom designed to really meet the demands of the final customer. Okay, types of sensors: the non-smart sensors, the traditional sensors, such as detection sensors, threshold sensors, the wireless low power sensors that are battery operated, that are very popular because everybody wants to go wireless, you know. And the problem with those sensors is actually that because the battery lasts only for a few days, if they are real time, they just work by extracting information a short period of time and going on deep sleep for sometimes 4 hours in order to get the battery last for maybe 1 or 2 years. Those sensors don't serve any purpose in industry, in our view. Of course, there are other approaches, we respect that, but in our view, real time is paramount in order to get industrial IoT. And finally, the road sensors, that they are, of course, very good for predictive maintenance, but they have a problem. And the problem is that they produce such amount of data that we're going to see this problem in a minute. But basically it relates to the database space and also the problem of post-processing garbage data that has no meaning and fouls the creation of prediction models. So smart sensors are here to resolve the problems of the other sensors. What is a smart sensor? Smart sensors are advanced platforms with embedded technologies that transform the traditional analog signals through digital insights. I love this definition. I think it's a good definition. The differentiation of the smart sensor, it's usually the main difference is the role with preprocessing, the computing power, the flexibility, and the adaptability to a particular task. And it's a disruptive technology that is going to change the industrial IoT forever, in our view. Topology of a smart sensor. A smart sensor is composed of different parts or subsystems. Of course, we have the transducer, which translates the physical changes into weak electrical currents. And then there is an analog stage that makes the signal conditioning, usually amplifies and filters the weak electrical signals into the levels that we need for the next step, which is actually to digitize using an analog to digital converter circuitry. And then is the microcontroller or microprocessor with, that makes the preprocessing with algorithms that improve the data quality, getting rid of garbage data, and that they provide what we call feature extraction. We will see that in a minute. Later on. Preprocessing heavily reduces the amount of data that the payload that is at the output of the sensor. And of course, we will talk more about the preprocessing and the algorithmics in a few minutes. Connectivity, wire or wireless, we have to forward the data to a node, usually, where the information is received from the sensor. And then sensors need power, you know. So we have to power the sensor either by the data bus with battery, internal battery, or using energy harvesting technology. Okay, this is a very quick review of the advantages of using embedded technology. We will have faster response time because we are closer to the sensor edge, which minimizes the latency on the system. We have a more reliable operation with intermittent connectivity. If the connection, for example, is lost for a few seconds, we will have a continuity on the data. It also improves security because the information is filtered and formatted in proprietary protocols that are very difficult to really hack. It's also cost effective because it saves payload, bandwidth, database space, and the processing is distributed over the IoT, industrial IoT chain. Embedded Edge preprocessing saves a lot of power on post-processing at the server edge. And also, it's a huge advantage of interoperability with legacy equipment because it's the way to go when all machinery needs to be connected to the new industrial IoT networks. So the Big Six. The Big Six is something that we we invent ourselves in our lab because there are 6 sensors that we see these sensors being used over and over. So the first sensor in our list here at the left is acoustic energy that measures the acoustic emission in the ultrasound spectrum. That measures the material stress in the machinery and gives the earliest warning of failure probability. The second and third sensors are very close together. In machinery with lubricants, measuring the lubricant contamination gives a good warning before something bad happens. Vibration is a very common sensor used widely in machinery monitoring. Although sometimes, and particularly if the sensor is not very good, the warning comes way too close to the failure. The fourth is temperature sensors or thermal imaging sensors. In some machinery, they can give a very good outlook on how bad is the level of energy lost in inefficiencies. Here at the right of the slide, we can see that when audible noise happens, it's usually way too late, and of course, when you see smoke, the manufacturing process is already stopped. You can complement those sensors with current and voltage sensors, and also you can read a PLC that controls the production process in order to get more additional data. So I like to remind that our target here is to give the earliest warning possible in order to replace the parts that are going to fail before it happens and then avoid the production stoppage. First case, acoustic energy. So we are in the Big Six. Okay. Some pressure wave is created when elastic forces change its energy state. It's all about energy, as I told before, with the digital twin. So detecting the stray energy, it's what we are doing with the sensors. And this is what serves the purpose of creating a prediction model. So the first thing that we use is acoustic energy by ultrasound analysis. And here I'm making a graph of vibration and ultrasound, so you will see the difference. Okay, for those of you that you are not probably experts in digital signal processing or signal analysis, the spectrum is divided into subsonic and audible frequencies, which are usually measured with accelerometers or sound pressure wave transducers. And those frequencies are below usually 1 kilohertz on the left side of the graph. And then on the right side of the graph, you have the ultrasound frequencies, which are beyond the audible frequencies. We cannot hear ultrasound. And they're measured with piezoelectric or specific ultrasound transducers. The interesting frequencies can go way beyond 2 megahertz. You see that part of the graph on the right side. This is an ultrasound acoustic energy sensor that we produce. This is the analog part. You see the transducer over there. This is the low noise preamplifier, the filtering, and it amplifies the signal to a level that can be actually digitized on the microprocessor platform that is also embedded and very small. So we will see the difference between acoustic energy and vibration in a minute. It's different. Both are a form of acoustic energy, but the indication and the energy that we're measuring is quite different. And we want to We're going to explain the difference in a minute. So regarding applications of acoustic energy, we have the detection of failure in gears, in shafts with misalignment, structural health in concrete structures, for example, and metal structures as well, partial discharge in substation transformers, other electrical faults such as electrical panels, pneumatics, hydraulics, fluid flow. There are many applications for this kind of sensor in industry. The advantage is the earliest warning. The cost is medium. Sometimes is medium to high, depending on what frequency band we are talking about. And the bandwidth payload is extremely hungry. And now we are showing a video clip regarding the use of ultrasound sensors in substation transformer predictive maintenance for medium and high voltage applications. Okay, this is a medium voltage transformer that delivers 40 kilovolts, and you are seeing the spectrum that here is basically ultrasound acoustic energy from 30 kilohertz to 90, 80 something kilohertz, and here you are seeing that ionization discharge happen and vanishes after that. The spectrum goes back smoothly to the normal one. And then I switch off the transformer. You see the noise signal to noise ratio is excellent. There is absolutely no signal when the transformer is off. And that's a big advantage of ultrasound compared to vibration. In vibration, you're going to experience a much worse signal to noise ratio. And we are showing here the two PCBs that are inside the ultrasound sensor, including the preprocessing unit that comes with the sensor. Then you probably are figuring out, okay, can we fingerprint each failure? Yes, we can, but it's something that takes a lot of work, of course. It's not easy, but it can be done, and we have done it. We can actually fingerprint failures by the fingerprinting on just by analyzing the spectrum, and this is a waterfall spectrum. For those that are not familiar, this is the C-axis is the time here. And yes, fingerprinting is possible, and in some projects it's very interesting to fingerprint the failures. So here, vibration. Vibration is a must. It's a physical variable that is very important to be monitored in industrial process. Here we have some definitions. There are two types of vibration. The free vibrations that are caused by a momentary disturbation, and the forced vibrations that are caused by an external excitation. The applications of vibration monitoring are really broad, you know, from rotating machinery, fans, motor, pumps, gearboxes, everything that creates a kinetic energy and that moves, rotates, creates vibration by definition. Vibration monitoring detects the stray energy that is wasted due to the inefficiency of the machinery, as opposed to the acoustic energy by ultrasound analysis that detects the stress on the materials. So that's a question often asked. What is the difference between acoustic energy by ultrasound analysis and vibration monitoring? And the reply is that they are monitoring different physical variables. And we have different versions of vibration sensors depending on the application and the frequency vibration range that we are trying to monitor. We produce sensors with sampling rates from 1 to kilohertz to well beyond the audible range. So this is a quick sensor demonstration of how vibration works. This is actually a sound pressure wave sensor. Sound pressure wave technology provides better sensitivity than accelerometers. In this example, we are comparing an accelerometer here. We have two fans where one fan has been modified to provide some kind of vibration. Two blades were cut, as you can see, and we are switching on both fans. The fans are very low speed, very low vibration, and as you can see in the oscilloscope, there is no real difference. So for this kind of applications where high sensitivity is needed, we opt to develop a vibration sensor based on a sound pressure wave transducer. And we are seeing here the undamaged fan running. We see the vibration on the screen, and now we are switching on the damaged fan on the left, and you will see in the yellow trace on the oscilloscope that there is a huge difference in the amplitude level on both fans. That was not visible before with the accelerometer transducer. Okay, and we are now showing on the small display the frequency analysis preprocessing, and you can see that the average vibration on the undamaged fan is almost none. And now we make the same check with the damaged fan, and you can see that there is a clear indication on certain frequencies are showing up on the display. There is one predominant frequency and some other frequencies on the display that are clearly detecting the imbalance of this fan. So vibration is a measure of the inefficiency of the system. Both are cases where we are detecting energy levels, but the application is different, and what we are getting from the sensor is a different thing. Audible frequencies usually don't serve any purpose because the industrial environments are so noisy that here in the middle, what we will have is probably a lot of noise. So it's very difficult to discriminate the noise from the environment to from signal from sensors. So lubricant condition sensors, we've been using those with machinery. So very briefly, we are discussing now the lubrication sensors, and there are basically two types of sensors. The first one, the one you see on the top right side of the slide, is an inline sensor that works with usually a laser source that measures the reflectivity of the metal particles on the lubricant. Of course, this kind of sensor needs an oil recirculating pump in the system, so there is a fluid flow in and out of the sensor. And the second sensor that we are presenting here at the bottom right side of the slide is a static sensor that works by attracting the contamination particles in the oil, and with an iridium magnet attracts the particles on the oil and gives you a very good measure of how bad the oil is going on and what is the wear and tear on the reduction gear. Lubrication and lack of lubrication causes many problems, and this is what we are detecting with the lubrication sensors. Thermal sensors, okay. Thermal sensors are very important in industry. Controlling the temperature on the process or the temperature of the machinery is a very important physical variable to be acquired and to be analyzed. Resistance RTD sensors like the PT100 are being used for many years to detect temperatures in industrial process. This is the sensor you see on the upper right side of the slide. They We hate them. They have high thermal mass, high inertia, very slow response to subtle fast temperature changes. We only use RTD sensors to control temperature in liquids. In contrast, the thermopile infrared sensors have high reading speed, sensitivity to subtle temperature changes, very low inertia, and they work very well as non-intrusive temperature control in solids. Finally, the thermal imaging sensors, they work like infrared cameras and create a thermal mapping of the industrial assets. Valuable information, but they're bandwidth hungry, so they use a lot of data payload at the output.
And this is a case with robotics, and we have made a zoom-in image over there, and you can see here the pics of one of the servos on that robot working. You see in the pics, this is the one process, one movement. You can see each movement of this robot with this kind of low inertia sensors. So again, modern thermopiles and modern imaging sensors can provide by infrared analysis a much better, much faster, and with time synchronization with the sensor fusion technology, you can actually allocate each peak, each temperature peak, with other peaks of vibration or some other sort of stray energy, and then create a model with that. Okay, this is a quick demonstration of a thermal sensor.
Okay, you can see here how fast, how low the inertia is on the sensor. The sensor is in this particular sensor, we were reading the sensor. It's 100 times per second, so the rate is 100 hertz, and you see how beautiful is the response to the change in temperature.
So the next sensor is the current sensor.
There are different technologies to monitor the current drawn by circuits or machinery. Depending on if you are monitoring AC or DC, we use in Ontario different transducers. Rogowski coils are used in AC, while in DC we use Hall effect sensors. You can make a good use of a current sensor, monitoring the current drawn by pumps, motors, rotating machinery in general, and monitoring the current. It's a very interesting parameter and a good complement to other sensors measuring. The cost is medium to low, depending on the application. They are not especially bandwidth hungry. Most applications, the sampling rate is 120 hertz, so they are not using a lot of payload.
It's a good point to have a current sensor on the DC and AC circuits on the factory. So the last one is voltage.
Some people believe that monitoring the voltage is an important parameter to control. In fact, for predictive maintenance, this is the last of our big six. We don't believe monitoring the voltage is so important. And let me explain the reasons. The extended use of variable frequency drives makes most of the voltage reading useless. So usually measuring the current draw gives a much better outlook of what's going on. And there are applications, however, especially in DC, where having a control on the voltage in real time could add some benefit to the prediction model. Okay, finally, the applications are motor pumps and any electrical driven machinery. The advantages are little, as we have discussed. The cost is usually low, and they are not bandwidth hungry. In most applications, the sampling rate is 120 Hz or below. So as a summary here, voltage indication is not like an early indication of anything. It has limited interest in early warning predictive maintenance.
So this is a quick recap of the big six: ultrasound, vibration, lubrication, thermal, current, and voltage. And just a quick insight of which is better for each purpose. And here, sorry. This is like a condition catalog that you can do in your project, and we do this kind of condition catalog very often. This is a very simplified approach, but this is what you do with different sensors, the actual condition that they are detecting.
And the best use of each sensor to detect different conditions. You can see also what is the earliest and the best indication for each kind of condition. And again, this is a very simplified approach. You will have to make your own research depending on the machinery that you are monitoring, depending on the targets that you have in your project, depending on the sensors that you are using, and the kind of machinery that you are monitoring. This table will of course change a lot.
But this is the beginning of the prediction models. This is how you start a prediction model from scratch. Okay, we're going to go over connectivity because a lot of people ask about connectivity on industry, and I'm going to be very honest about that. IoT and sub-gigahertz wireless such as Sigfox or LoRa serve no purpose in industry, and the reason is they don't have enough bandwidth to send anything that really serves any purpose. As I told you before, sending temperature every 30 minutes doesn't make any sense on industry. You need a stream of continuous data to be forwarded to the database, and then those systems, they don't have enough bandwidth. They have so many time restrictions that they don't serve any purpose.
So as a preliminary summary, industrial IoT cannot rely on IoT wireless. Well, we can use some other systems. We can discuss anything from SMS, Bluetooth, narrowband IoT, Wi-Fi, and 3G, 4G. And generally speaking, we cannot consider Wi-Fi as a connectivity solution that works in industrial environments. The bands, especially the 2.0 giga band, is overloaded and clogged with so many services that is not really a solution for industrial environments. And we also have the Bluetooth, which has medium bandwidth, no timing restrictions, but the coverage it's usually really bad. 60 feet, many times much less than 60 feet. And there is something promising, that is Bluetooth 5.0, that improves the coverage by 5 to 10 fold. And we are developing our own Bluetooth 5.0 solution for short-range connectivity, and we believe it's a good solution for some applications.
3G and 4G is a good solution, but it comes with a cost, of course, because data, you have to pay for the data, you know. And 4G provides more than enough bandwidth to send most relevant information over wireless. It's a good solution depending on where you are, because some places there is no coverage, of course, so you have to check out what is your solution. Sometimes you have to mix one solution with another. You can actually get Bluetooth 5.0 on a local area network, and then get the data out with 4G or something different. And 5G. 5G is very interesting. There is a lot of hype. It's going to change our lives and so on. Okay, the 5G that they're installing here, Verizon, AT&T, and so on, is not the real 5G, I have to tell you. 5G is a combination of 4 technologies. And actually, 5G has some years to come. The real 5G with 1 millisecond latency, the real 5G with the very awesome bandwidth and so on. The 5G that they're installing in Europe, in the US, is probably 3-4 times the bandwidth of the 4G, which is already a good system, and it doesn't have the features of the real 5G that uses technologies such as massive MIMO, which is a set of huge antennas that sectorize the cellular coverage. And actually, the problem with 5G, the real 5G, is that it takes a lot of money and time to install, because they will have to replace the electronics and all the antenna sets in all the base stations. So it's not for tomorrow.
And so the next slide is a quick recap about connectivity, but a question that we heard from time to time, is 5G, is the 5G technology replacing the need for preprocessing at the sensor edge? And our answer is a big no. 5G, it's an expensive technology that is going to take many years to be deployed, and except for private networks, is not a solution that is going to replace the need for preprocessing at the sensor edge.
Just with the next slide. Why industrial IoT is different? Okay, basically the bandwidth, because the real-time requirement, the variables that we're measuring, they're hungry, they're really hungry on data, they're really hungry on bandwidth, the payload is huge, and we want to see the problem now, discrete data versus continuous or time series data. There are 2 different worlds, and you have to homogenize the data in order to actually work with that. And machine learning models, they don't really work if there's too much garbage. So you need to simplify the data at the origin.
Okay, the problem of too much data, here we are presenting 2 slides. First is, as said by General Electric CEO in the 2012 Minds and Machines conference, 20 industrial sensors deliver 1 terabyte of data per day. And the second issue that we would like to discuss on this slide is actually that getting more data does not solve anything. And that's the reason we are against raw data. And here on the second slide, we have a few jokes about the problems of getting too much data. Actually, getting too much data is not a joke. It's a big issue. It's a big problem that preprocessing and embedded edge technology results. And I would like to remind something that sometimes I think is forgotten. Is the hidden cost of processing at the server edge too much data. There is a cost that you have to evaluate. You like to follow that approach.
And here we're going to go very quickly over the problem.
And it's the problem that represents the process of what is called continuous unstructured or time series data. Here at the top right of the slide, you see temperature data that is discrete. So it's a piece of cake to put on a data set. And there at the bottom right, you see a vibration waterfall fast Fourier transform spectrum signal that represents a very good example of unstructured data.
So you see that these are two different worlds. It is impossible to process both things with the same tools. So what we do is actually, okay, with temperature, for example, simple example, we prepare a data set that we put on a database, right?
And with comma-separated values, or CSV, you can create a discrete data string. That's not rocket science. This is something you can do with an Arduino. But unstructured data here is a different animal. This kind of complex data is very difficult to feed on a database along with the other discrete values, such as the temperature example. In order to put both discrete and continuous data in the same database, you need first to homogenize continuous data and provide a structure that is similar to discrete values. But this is not the only problem. On the other hand, even if you have a special database for continuous data, you will have to learn a lot about digital signal processing in order to understand the data and use machine learning with success. So here we are presenting our solution. Feature extraction. By using hard-coded or neural network algorithms, we extract the relevant information from the signal, including the underlying information that is relevant to the process. Then how we do that is proprietary and out of the scope of this presentation. The heavily reduced number of variables is then stored as discrete values, creating a data set that is very similar to how we store discrete data.
So here is an example of what we're doing with preprocessing. In vibration, we have 97.5% less payload than the raw sensor, and in acoustic energy, it's 99.6%. So what we're doing in practice is replacing the acquisition systems that are PC-based or in a rack with acquisition, National Instruments or whatever you put here, with a computer. And we're replacing for something that is 28 millimeters long by 30 millimeters width. Those are zooming of real boards that we have in our sensors. This is the acquisition ultrasound part, the analog part that I showed you before. And this is the processing microcontroller. We have 3 platforms, from a small one to a medium processing one, and one that is very powerful for ultrasound. So depending on what we're doing, we put a different processor. And this is an example of a finished sensor that the enclosure is actually less than 100 millimeters. So we are replacing the heavy and bulky and expensive acquisition system for embedded systems with, I would say, more powerful features than the normal systems.
So this is a quick recap of the advantages that we are presenting here regarding embedded edge technology. It resolves many problems that we have been discussing in this conference, such as connectivity, data homogenization, clogging database with terabytes of users' data, and how to resolve the issue of the machine learning models that don't work by getting rid of the garbage data that makes the modeling almost impossible. And then we are coming to the last part of this presentation.
Case studies. This is the better part, maybe, of the presentation. Okay, case study 1, that's a steel plant, and they have a problem.
The process involved the hot dipping galvanized of large rolls, but scattered scratches on the metal sheet result on entire rolls being rejected.
So this is actually what they sent us. Those are the scratches. You see the scratches over there?
And the problem was costing the plant a lot of money per year, The rejected rolls were sold as scrap. So our proposal was detecting the scratches with acoustic energy by ultrasound analysis, and we are presenting now a video on how we make that research.
Okay, we are scratching the same metal sheet that is galvanized with a dentist tool, and you see a peak clearly here around 25 kilohertz, 25 to 30. So we do many trials with the same, many checks, different pressures, even different tools, same peaks, same frequency. It's not dependent on how heavy are you with the metal. It's something that is, I would say, it's relevant to the metals in contact, to the stress. And this is, I'm barely touching, and the guy on the right side, the one scratching. I was barely touching the metal. We couldn't hear anything because it was, and you see the same peak.
So detecting even very slight scratches in metal sheet fabrication can be done with the help of acoustic energy sensor. Case study number 2. This is a textile laser processing. Today most of the blue jeans are textured with laser and they're not stone washed anymore. That makes the process much more environmentally friendly as no water is used or polluted in the process. But here's the problem. As a result of external vibrations caused by the plant operators, the laser got out of focus and some batches were rejected. Our solution was the use of a triaxial vibration sensor that disables the laser shot in presence of vibration, ensuring top processing quality all the times. Okay, case study number 3, wind generators. The wind generator towers are getting taller and taller.
Then the problem is you have to replace 25 gallons of oil over there, and that depends, the oil depends on actually how bad is the reduction gear and what were the wind conditions on that particular year. So replacing the oil when it's only necessary is something very interesting, and there are many projects about real-time condition monitoring on wind generators that save a lot of money in maintenance and also in resources.
Okay, case study number 4. Production robots in the automotive industry. 6DoF heavy robots are widely used in the automotive industry. As they are getting older, the possibility of making predictive maintenance becomes more relevant. As explained before, each stoppage minute in the automotive industry costs $20,000. So our proposed solution here to reduce the stoppage to a minimum was to fit in the robot 5 different sensors attached to each axis. A total of 30 sensors monitor the robot health condition in real time. Here is a short video shot while getting the first data. Vibration, ultrasound, oil condition, voltage, current, and temperature sensors were fit into an ABB 6DoF robot. We are deploying the graphic user interface here. That's the gateway and the local server. That's the graphic user interface. That's developing Grafana. The robot was put on a heavy movement program so we can get data as soon as possible. The data is updated every 70 milliseconds. So here's case study number 5, transformer substation predictive maintenance. We started this project as requested by several utility companies. The target here was to design a predictive maintenance system that works with electrical distribution transformer substations, with a special focus on assessing the real condition of the transformer by measuring the partial discharge phenomenon. There are two ways to measure the partial discharge phenomenon. One is measuring the UHF, ultra-high frequency emissions.
The other one is ultrasound. We found the ultrasound to be much more effective, better signal-to-noise ratio. There is no external interference that could affect the readings, and there is a lot of research on that particular field, and there is a lot to be done in partial discharge research and substation maintenance with utilities.
Here at the left side of the slide you can see a real prototype developed in Poland and Canada in 2012 as described in an IEEE paper.
You see the industrial PC and the acquisition system over there. The rack is huge, it's heavy, it's impractical. You cannot put a rack like this on a utility. They will kick you out, of the project. So what we do is actually do the same thing with pre-processing on a sensor that is 100 millimeters or less.
On that small enclosure we have the ultrasound transducer plus all the digital signal pre-processing on a compact and cost-effective solution. Compared to what we have on the left side, you see the rack, the acquisition system that we mentioned, and the transducers are actually in the top of the rack, as you can see here. The monitoring system completes with some other sensors such as infrared imaging and some other secondary sensors such as flood and intrusion detectors. We are showing here a proposal for a graphic user interface developed in Qt. The target here is to assess the condition of the transformer station at a glance and provide trending indication here on the right side. So we create here some predictive model indication on the right side, and there is also the environmental and acoustic emission, thermal emission sensors, which are the main variables to be controlled in this project. And also we have a sensor fusion display here on at the right bottom side of the slide. Quick summary here, smart sensors are paramount to get production and machinery condition data. Raw data from industrial sensors produces a huge non-homogeneous payload. Machine learning models only work with relevant data. So our solution to the industry is to provide smart sensors with embedded edge non-destructive preprocessing that perform feature extraction as explained in this presentation. And finally, a word of caution about what we call machine learning quackery. Some startups are offering built-in predictive maintenance models without sensors, based only in production data provided by existing PLCs at the factory.
Honestly, this is like selling snake oil or I don't know, quackery. I don't understand how you can get actually a machine learning model, any solutions for the industry with PLCs, which they don't give you any information. Sensors is the way to go. So actually, thank you very much. It was quite long. We may have just a few minutes to reply if you have any questions about that. And if you refer to a particular slide, I can go back and try to reply if I don't remember the issue. So thanks very much.